Welcome back. This is my video on Holt's linear trend method. So to put this into context, my previous video introduced a very important idea, and the important idea was that of exponential smoothing. The basic idea of exponential smoothing is that we're going to average previous values in order to make our forecast, but we're going to have a smoothing parameter that allows for these weights that I use in my weighted average to decay. So we give a lot of weight to the most recent observation, less weight to the observation before that, and then these weights are going to trickle off down to zero as we go further and further back. So we just want to give more weight to the nearest neighbors. And I said this method is great as long as you only have a cyclical part present. Well, what if you have a trend or seasonality? So the answer to that is we're going to use this Holt's method, which is going to allow us to have a linear trend. In my next video, we'll capture the seasonality component. So a couple things about Holt's method. It has a number of names. So another name that it goes by is double exponential smoothing. Sometimes you'll see second order exponential smoothing in different textbooks as well. So all of these mean the exact same thing. And so the whole idea is that if there is a trend present, we can do better than just estimating the current level. So let's go over to my document camera for a second. And let's say that this is time and this is my y variable. And so maybe we have a time series that looks something like this, and I'm trying to make it so that there's a trend. Now, what we would do with simple exponential smoothing is I would try to estimate the level at my last observation. So call that capital T. That's my last observation. And that level would be a weighted average of the previous cases. So I'd give a whole lot of weight to this y value. I'd give somewhat less weight to this one, a little bit less weight to this one, and so forth. And this y value would get essentially no weight with an exponential smoothing. So then the level, so let's say that this is the level at time t, is just my summary of everything that I know up until now. And so if I'm doing simple exponential smoothing, my forecasts are simply going to be this level. Well, the idea with this Holt's method is that if I want to go h periods out from some time period t, what I'm going to do is take the level at time t plus h times some slope estimate at time t. So I'm going to do the same thing that I did in estimating the level to estimate the slope of this function. And so at this point, I'm going to have some slope, and maybe that slope estimate looks something like this. So this is my current slope. All right, so just to make this really clear, let's say I have a run of 1. This would be b capital T. And so that would be my slope at time period t. And so the whole idea of this equation is that we're just going to take the current level, and if I want to go, say, 3 periods out, then I'm going to take 3 hops of size bt. All right, so this would be my forecast. This would be y hat big T plus 3 given the information I have at t. And so the whole idea is take your level at time big T and then take 3 hops up of size whatever this bt is. And so that's the whole idea of Holt's method, is just go up however many slopes you need to, meaning however many h's you have. That's the forecast equation. How do we get this b sub t? Well, we called it double exponential smoothing because we're going to do exponential smoothing on the level. And so this is the level equation. Here is your trend equation. And so let's go through these in detail. So my level equation is just going to give weight alpha to the latest information, and it's going to give me weight 1 minus alpha to my predicted value of time t. So what's the predicted value of time t? Well, it's going to be the level I was at time t minus 1 plus 1 slope of what I had back at time t minus 1. So in my picture, if this is t minus 1, well, let me kind of draw it again. We're going to make it really simple. And if this is time big T minus 1, I'm going to have some level, then I want to go 1 slope out. So that's B big T minus 1 would be my forecast of the next period. All right, so it's exactly the the formula we had before. This is the new information. This is my prediction of the of where I should be at time t. So think of this as the forecast of where I should be at time t, given information at time t minus 1. All right. Well, we're going to do something really similar with the slopes. We're going to have another smoothing parameter, which I'm going to call beta. The textbook calls it beta star, but I don't see a need for the star, and I think it just confuses things. So I'm just going to call it beta. And so what we're doing is smoothing the differences in the levels. So I like to think of this as like a first derivative. This is what is my change in y, my expected change in y, and you could think about dividing this by 1. So this is your rise divided by your run, gives you the current slope. So this is like the current change, and we're going to give that weight beta. Then we're going to give weight 1 minus beta to the previous value of the slope. And so in essence, what we're doing is forming a geometric series where we give less and less weight to previous slope values. All right, so now we have two smoothing parameters. We're also going to have two starting values. So we have to pick the starting level as well as the starting slope. And so, as I said in the previous lecture, you can either take some values for this. For example, you could just take a starting slope of 0 and take the starting level to be the average of the first few values. Or you could have them estimated by the model. So by the default, the default is to estimate them using least squares. This is exactly what I said. The current estimate of the slope, so that's the current estimate of the slope, is just an exponentially weighted moving average of the changes in the level. So that's a change in the level. You can think of this as the summary of all the previous changes in the level, and we're just doing an exponentially weighted moving average of those observed changes. Another way to think about this is we're really smoothing two things. We're smoothing the position, or the level, and the derivative. So the position and the derivative is kind of calculus language, but that's the way I think of it. And that's, by the way, why it's called second order exponential smoothing, because we're not just smoothing the level, we're also smoothing this derivative, the change function. All right, one more thing. The drift method is, you can think of it as a special case of this, where what I'm doing is giving equal weight to all of the one period changes in y. So all of those count the same. The first change that I observe counts the same as the last one. And then what happens is I'm using the naive, most recent level to give me my, my L at t. So L at t is just y at t, and then drift is just averaging everything else. So I find it kind of helpful to connect this method to the methods that we've studied previously. Well, how do we do this in R? I'm going to use another data set. This data set comes from a Kaggle data set tutorial on, you'll see here they call it double exponential smoothing, but that's what it is. And in this tutorial, they use a shampoo data set, which is kind of similar to what we'd be doing in a marketing role, where we're trying to predict our shampoo sales in the future. So I need to know how much to produce, how much to ship to my retailers and distributors. And so these methods get used a lot by brand managers. And so if you go through this tutorial, they're doing basically the same thing I'm doing, but they're showing you how to write it in Python if that's of interest to you. All right, so we've got this shampoo data. It's monthly data for 3 years. I've looked at some of the diagnostic plots, and there's not a lot of seasonality with this, and so therefore I feel it's okay to use Holt's method on this, since there's not a lot of seasonality. If there were seasonality, we would need the Holt Winters method that I'm going to cover in my next video. Well, the first thing that I see when I look at the data, so here's the data set, is we actually need a little bit of a Box-Cox transformation. It doesn't quite require a log, but this lamb was computed with the Box-Cox function, boxcox.lambda function. So I'm just going to use that throughout the example. To fit one of these Holt models, R provides a wrapper for a much more general function that we're going to study in a couple of videos from now called Holt. And so with Holt, you can specify the number of periods ahead and your Box-Cox transformation value. And here's the output you get. So you're going to see we've got our Box-Cox value. Here are the estimated smoothing parameters. So when I see these smoothing parameters, what's notable is how small they are. And what that tells me is there's not a lot of changes in, for example, the slope. So let's just start out with this. The slope is not changing much over time, so I don't need to give a lot of weight to the latest change. If the function had a rapidly changing slope, then you'd want to give a lot more weight to the current change, and beta would be much larger. Likewise, we're not going to, after accounting for the slope, there's not a lot with the alpha that we need to do, so we get a very small value there as well. So these values have been picked by the Holt function to minimize the sum of squared errors. It's also chosen our initial values for us. So here is the initial slope and the initial level, and it gives us the error. What comes next are the forecast values. The forecast values you're going to see are increasing, and we can produce a plot comparing, say, the Holt method with the drift method. And so the Holt method, I think, is kind of interesting because the slope of the forecast, so the slopes are just going, following a line in the Box-Cox scale. The Holt forecasts are steeper than the drift method. So remember, the drift method, in essence, draws a line from the first point to the last point and extends that line. And what the Holt method is saying is you can do better because it looks like maybe the slope is increasing a little bit at the end. And so that's why we are choosing a non-zero value for beta here. But since the slope is kind of increasing towards the end, the Holt method picks up on that, and it allows the slope to get a little bit steeper. All right, I want to cover one more extension of this, which is turns out to be one of the better approaches in practice. It's called the damped trend method. And so the basic idea of the damped trend is to have our forecasts flatten out as we go off into the future. So let's go over to the sketch pad for a second, and I'm just going to illustrate this with a little picture. So if I have some time series like this, here's my time series, and I go off and I fit my trend, and so say here's my level. The forecast with the Holt method is just go straight. So this is going to be the forecasts with the Holt method. Perhaps I should capitalize Holt since it's a guy's name. The idea with a damped trend is this. We're also going to increase, but the change in slope is going to diminish over time, and eventually it's going to become flat. So maybe my forecast looks something like this. So this would be this was supposed to be completely smooth here. My pen didn't quite work right there, but this is going to be the damped forecast. And so that's the whole idea, and this is going to flatten out and approach some limit. So this will approach a limit as h increases. So as h, the number of periods I go out, increases, this is just going to approach a limit. All right, so how do we do this mathematically? That's the basic idea. So this is the forecast equation we're going to use. So take the level at our last value in time. So wherever we're at right now is time period t. Take our level, and then if you want to go h periods in the future, we're going to add a geometric series of phis times the current slope. And that's going to give us our forecast. So this phi is called the damping parameter, and it's something that R will either estimate, so the Holt function estimates it with the damped equals true argument, and it tries to use it. It uses some cross-validation, and as long as the damping part improves your estimate, it uses the damping part. If it finds that the damping doesn't help you, then it just goes back to Holt's method. Or if you want to specify a certain phi value, you can add the argument phi equals 0.9 or whatever you like. In practice, let me just mention this decays pretty quickly, so we usually would never choose a phi less than, say, 0.8, which is what the textbook recommends, and I agree with that. A couple interesting special cases of this are, whenever we set phi equal to 1, then I'm just back to basic Holt's method. So let's just think about why that is. So if I have 1 plus, well, 1 squared is 1, plus 1 cubed, which is 1, all the way 1 to the h is 1, I would just have h copies of 1, which is h. And so it would be LT plus h times BT, and that's exactly what I have here. So that complicated geometric series would reduce to just h. So that's one interesting special case. Another special case that I think is kind of interesting to point out is if I were to take phi equal to 0, so then I would get 0 plus 0 plus 0 plus 0 h times, and in essence, this whole term goes away. So the sum of 0 h times is 0, and I wouldn't account for any current slope at all. And so what that really means is I'm doing simple exponential smoothing. So Holt's method and SES are both kind of extreme cases of this damping forecasting method. All right, now I mentioned that the forecasts are going to approach a limit. Well, what is that limit? It's another geometric series, and so let's just go back to my document camera. I stated in my previous video, here's a geometric series, and what you learned in possibly high school was that the sum of this is whatever this constant is divided by 1 minus whatever this r is that's getting raised to the power. So what do we have here? Well, we have b sub t times phi plus phi squared plus all the way through phi to the h power. And so this is this part right here. And so the question I'm going to ask is, what happens to this when t gets really big? So I'm going to factor a phi out, and so you get bt times phi, and then you have 1 plus phi plus all the way through phi to the h minus 1 power. And think of this as the a term, and then phi is the r term. And so if we take the sum is a over 1 minus r, in this case it's going to be bt times phi divided by 1 minus phi, and that would be the sum of this geometric series. And so that's what I've given to you right here. So that's what happens in the limit as h gets really big. So if you want this in English, short-run forecasts follow a trend, this increasing or decreasing trend, whichever way BT is going to take you. But the long-run forecasts approach some constant, as they did in my my picture here. So you can think about, this is your LT. And then this is that constant right there. That's how much this thing goes up by, which is exactly what's written here. Okay, the smoothing equations have a very slight modification from what we had before. And so what we had before, let's go look at those. With Holt's method, we took the previous level plus the previous slope estimate. And what we're going to do here is it's basically the same thing, the previous level plus the previous slope estimate, but remember we have to dampen that. And so we multiply it by 1 phi because we're just going one period out. And then likewise down here, we do the same thing, we dampen that value. Well, let's look at a couple examples now. I went back to the shampoo data set. My code is over here, so maybe I should start out with the code. And I forecast the future value out 24 periods. I'm going to apply the Box-Cox transformation first. And let's compare Holt method with the drift method with the damped method. And by the way, I'm going to use a fairly aggressive phi of 0.9. And so that's going to dampen it fairly quickly with basic simple exponential smoothing. And I think this picture is very clear in terms of what happens with these methods. So as we saw before, Holt's method picks up on the fact that the slope is increasing towards the end a bit. And here it looks like it's a bit flat and that it increases. And therefore Holt's method projects out as a line into the future. The drift method is also going to project out as a line, but it doesn't pick up on the fact that the slope is changing. But let's go look at our damped method. So the damped method, you'll see, starts out increasing really close to the same rate as the Holt method. but then you'll see it flattens out. And I think it's kind of clear that this is approaching a limit based on the math that I just did, while the simple exponential smoothing method makes no attempt to capture any trend, and it's just flat. So I think this picture should make the difference between the damped trend and a normal Holt linear trend model very clear. I want to do one more thing with you, which is let's have a test set. So with this test set, I'll use the first 2 years as my training set, and we'll fit the same 4 models. The only thing I'm going to do differently this time is I'm going to let R pick the phi value for the damp method. And so this is how quickly the forecasts decay. Moreover, I'm going to use the last year as a in the future test set. Well, let's go compare the accuracy of our methods. And so what we see is that Holt and drift actually do about the same, both in terms of RMSE and mean absolute error. In fact, it looks like drift is actually doing a little bit better. Not by much, but maybe a little bit better. And I warned you back in week 1 that very simple drift method is often hard to beat. And here's a case where it actually beats this much fancier Holt double exponential smoothing method. But when we look at our damped version, and by the way, R chose a much less aggressive damping coefficient, so 0.98 means it doesn't decay that quickly. But just that little bit of decay helps us a lot, and it cuts the mean squared error and the mean absolute error, by more than half by having that damped trend. So that's a big deal. Of course, the simple exponential smoothing is a disaster. So the test set errors are pretty poor compared to the other method. You shouldn't be using simple exponential smoothing here because you have a trend. So that's kind of an important lesson. You need to identify what components are present in your time series and then use an appropriate method. So since there's clearly a trend in this data set, Holt, drift, or damped would all be appropriate. This test set is suggesting that the damped method is the best. All right, that's it for linear trends. In the next video, we're going to cover seasonality.